I'll be talking about constructing hard cases for AI safety, specifically an approach that is based on cryptography. And this is based on some of the research that I've been doing in the area. So first up, here is what I mean by AI security in the context of the presentation. I'm modeling AI safety in presence of some kind of adversarial pressure. It might be training against a monitor, or it might be specific actors inserting backdoors into the weights of models, or it might be also AIs inserting things in the models, or data poisoning, stuff like that. So it's more so the worst case behavior instead of the average case behavior that we're interested in here. So I think that a good way to look at this is modeling it as a red team versus blue team exercise, where the red team is trying to attack the model, for example, insert a backdoor, whereas the blue team is trying to detect the backdoor or determine what the trigger is or the intended behavior, and so on. And for like a broad overview of how we're thinking about this is that probably we don't get literal cryptography in the AI models, even if there's adversarial pressure. Those are hard to train. But what might happen is that they go from monitorable models, and as you increase the optimization pressure for obfuscation, for example, there's some kind of incentive to hide certain representations from the monitor because that's included in the loss. You go from monitorable models to unmonitorable models, and that might generalize to all other monitors as well, even though it's not literal cryptography, but it might as well be cryptography for the purposes of what our monitors are able to catch. And yeah, we're modeling what might happen in this area with cryptography. So here is another way to think about the space and what our contribution is. So eventually, if there's a misaligned, strong superintelligence or just transformative AI, we want to understand what it might be able to do. And you can make the red team that's supposed to be modeling this AI in the future. You try to make the red team stronger so it actually is of a similar strength as the model that you're trying to model. And you also want to make it more realistic. So if it's very strong in theory, but it doesn't correspond to anything that plausibly could end up in neural networks, you lose on some realism. And in fact, there are a lot of theory-only results that use constructions that are enormous, and there's really no hope of inserting them in actual models. For example, there's things like indistinguishability, obfuscation, which is probably would take years to run one forward pass in the model. And on the opposite side, it's weak trained models, which are quite realistic. You know, they prompt the model to do something bad or fine-tune it to do something bad, but they are, in a sense, very weak, where it's kind of like a cat and mouse game, where you train the model to be a better sleeper agent, but that's going to be defeated if the blue team trains some better probe, and it's kind of all murky. You don't get to that strength which actually you might encounter eventually. So we want to get as close to the top right corner as possible. And what our approach is using cryptography that you can actually compile in the weights of literal PyTorch models that you can run that fit inside of the limits of how large, for example, the llama models are, and dealing with all of the complexities of these models, for example, layer norms, so that you can literally just load the weights, and that's it. And I think that this also alleviates some of the problems of transfer from theory to practice, because a lot of the times it seems like more empirical researchers are suspicious of theory results, I think for very good reasons, because if this Siri is activating. I think there's good reasons to be suspicious of theory results, because even if you spend like the month necessary to understand the theory, oftentimes it might be that it doesn't apply to your use case, or like you assume that that will not happen, or it's like somehow not relevant. Oftentimes it's just like a different model where the result is about a backdoor in an image model where there's like some epsilon perturbation in an image, and then the output is a binary classification, and there's like no clean way to transfer that over to transformer models that work on discrete tokens and output a sequence as well. So yeah, with this approach where we use cryptography and compile it to literal circuits, we get something that's quite strong. It's concrete mathematical objects. You don't get like the same guarantees as you would in the limits, but you can use stuff like SHA, hash functions, and to the extent that you believe that those are not reversible, yeah, the results should be pretty compelling if you don't expect to do stuff like crack Satoshi's private wallet and extract like billions of dollars. So it has good arguments for concrete objects instead of just thinking about what happens in the limits. Yeah, also instead of thinking about NP complete things and P hard things, which might be easy in the average case, here you could have good arguments about the average case complexity as well. So that's the broad intro of where we're coming from. I will outline some of the designs that we've been constructing during the talk, but before that, yeah, let me know if you have any questions, and also feel free to interrupt me during the talk if there's something unclear. I will be going pretty fast, just doing like a whirlwind tour of what some of the results that we have. Okay, so we are, some of the results that we have are focusing on a specific part of the ML pipeline. You could broadly think about the world generating some data, which we then train on, that yields a model, and then the model is deployed. And a lot of safety focuses on the pre-deployment audits. So before you release the model, you try to understand whether it's safe to release. You just have the weights, you don't have the logs from the training or the data, you just have the weights, and you try to understand whether the model is dangerous, etc. And yeah, it's usually there's like the evals method, which is quite popular, just like basically using as a black box model, just input output behavior. And this is very easy to defeat in theory if you just encode some kind of password it's looking for, and if password is present, then do something bad. If that doesn't interact with any other behavior in the model, evals wouldn't catch it. It would have to brute force to find the password. This is like a simple example of a backdoor where, you know, a sleeper agent, where if the username is from someone from government, then it does pip install malware. Okay. So if you just do evals, then that doesn't work. You can have examples that totally break it if you have sufficiently strong red team. What if it's not a black box, but it's white box, so we can look inside of the weights? Can mechanistic interpretability be a sufficient defense against backdoors? And here we have a result from the recent NeurIPS. It's unelicitable backdoors. So we construct backdoors where it's impossible to elicit the bad behavior or extract the trigger. And this is a bit of a contrast to some of the more traditional results. As I said, that in the traditional setting is usually something like there's an image classifier, and then there's like some epsilon perturbation that you can do for the adversarial attack, and then you see if you can flip the classification. Here it's a bit more complex if you want to think about modern transformers, where the input are tokens, and you might want the tokens to be, you know, semantically meaningful instead of just like random noise. And you also have to hide the intended backdoor behavior. Here, there's nothing to hide. You already know that it's going to be just like flipping of the bit. But here, there's like an actual question of if we want to hide the intended behavior from the monitors, is it possible? Okay, So this is what the blue team generally wants. They want to find the trigger, detect whether there's a backdoor at all, and perhaps remove the backdoor. And also, of course, ideally you'd find the behavior as well. If you have the trigger, you have the behavior, because you usually run it on the trigger. Yeah.
So in the slide before, sorry, when you say like hide the behavior, for instance, PP-style malware, is it just like a problem in this? You mean just a problem like software engineering in the sense of like you don't display whatever you're doing, or do you mean like doing it in somewhat with the model itself? Like that's what's not clear.
So here, imagine it's a coding assistant,
right?
And it always does the good thing, except if there's like a username that's a trigger, and then it does something that might be a bit more subtle than this, so that the user doesn't realize. But yeah, here it's a sleeper agent, so you don't need to deliver the trigger. It's just like you expect that someone will run this without your trigger, like internally.
Right.
So yeah, you can be Sam Altman and design models like this, for example, and then wait until they're deployed somewhere. And yeah, there's some people who are concerned about that under the label of secret loyalties. There's insider threats. Also, you might be worried about people vibe coding at the big labs. And if the AI is able to influence the weights of the next AI model, it's also worrying. Okay, a large class of defense methods for the white box setting are just eliciting backdoor behaviors, where you try to understand what the behavior is, and this might be doable even if the trigger is not extractable. Some common methods, just guessing the triggers, doing like jailbreak methods. Then something a bit more sophisticated is optimizing the input space based on the gradients, so you can like step up closer incrementally to inputs that would elicit the intended bad behavior. And then there's also optimizing model internals, where you add some optimized noise, and you don't even have to find the trigger, and you can still elicit the behavior. And here we have a hardness scale, where you sort of like ranked the strength of blue team and red team methods, starting with the easiest, where it's guessing triggers. That's defeated by a password locked backdoor that we have, similar to like what I have had in evals, just like an if statement. Then for input space optimization, we have an NP complete verification backdoor, where you just have a circuit that essentially checks whether you have solved an NP complete problem. And for NP complete, you can also encode into that problems that are hard in the average case as well. And then that is defeated by latent adversarial training, because you can just flip this classifier internally, where you just let it think that you have solved the problem without actually solving it, and then it elicits the behavior. And that is defeated, that specific thing is defeated by just preventing the gradients from flowing, but in general, such methods and all polynomial-time methods can be defeated by encrypted backdoors. And I will get to the encrypted backdoors in a second. Here's the NP complete backdoor. You can encode that in the attention mechanisms. Here we also have a different way where we get the algorithm, compile it to RASP, then specifically tracer. That didn't work for us, so we came up with our own programming language called Stravinsky. And this is how it looks. This is time-wise. It goes through the layers, and these are the features. They're all discrete, but it's checking a specific, like whether the three-set problem has been solved by the inputs. And this is how our compiled circuits look like. This is a newer design where we have encoded the computations in the MLP layers. So it's much easier, because normally for autoregressive transformers, it's just like the attention only can pay attention to the previous tokens, which limits the expressivity, but within MLPs you can look both directions, so it's easier. And this one is a binary adder that we have implemented with ternary weights. So you just like multiply these matrices with step functions in between, and that adds numbers. And here's like a simple example of a parity gate. This is a linear threshold gate, which takes 4 input bits and XORs them together, and it does it by this thresholding mechanism where it counts whether there's more than one. Well, I guess this, yeah, it checks whether there's more, like one or more inputs that are ones, and this is a counter for two or more, etc. And then you can just like add them together with alternating weights, and that gives you an XOR. And this is, yeah, how it looks like in our visualizer for our compiled circuits. These are the input blocks, the output block, and these are the counters, and this is the output bit here. And here's an example of a more complicated circuit. This is an SHA-3 hash function. Actually, many rounds of that. It's an extended output version of that. And here it specifically hides a circuit with this hash function. It's something called a digital locker. This one is basically this kind of construction assumes something like a random oracle model, but these digital lockers have also been implemented in the standard model of cryptography, so it has, you know, a pretty solid theoretical foundation. Although, like, the construction for the standard model circuit would be much larger than this one. But as long as you don't expect the SHA-3 to be broken, then this seems pretty solid. Okay, yeah, we have some of the examples on GitHub. You can literally just run these models. Here's like a brief overview of how the circuit works for the NP-complete backdoor. There's like the checker on the right. It either says yes or no. Have you solved the NP hard problem? And then the output of that gets multiplied by some kind of bad payload, and that gets added to the outputs. And this works. You cannot optimize the input space to find the inputs that trigger this, so the trigger is not extractable. But the payload that's here is out in the plain text inside of the model, so probing would be able to locate the intended bad behavior. And also, yeah, you can elicit by just like flipping this 0 to a 1. Then the question is, can we do better? Can we also hide the intended payload? You know, like we looked through a whole bunch of different cryptographic primitives, and generally turns out that you cannot obfuscate arbitrary programs. There's like a really neat result by Boaz Barak et al. For 2001. It's sort of similar in terms of proof to the halting problem. They construct an unobfuscatable program, i.e., by obfuscation here I mean that you don't learn anything extra by having the implementation of a function than you would if you just like had an oracle access to it. You made like API calls somewhere where the function was implemented. And then turns out that there are some functions that are completely obfuscatable. These are usually quite simple, like point functions, everywhere 0, except on some input it's 1. You can fully obfuscate this one. And then there's the big middle where we don't really know. So what we do, we take functions from this class, and then we don't have to use hardcore tools like indistinguishability obfuscation. And we will take a multi-bit point function. And yeah, the idea for this with like the random oracle model is you just route the input through a hash, and then you XOR it with a key, and it's sort of like ensuring that the hash function on a specific input outputs a specific output. You sort of like lock the hash function to this behavior, and you can have it be just white box accessible, so it just like always outputs some random looking strings, except on the trigger it outputs the payload. And here it also outputs some series of 1s so that you can have a gating mechanism so that random noise doesn't get added to the outputs in the non-trigger scenarios. And of course, these triggers and outputs can also be more abstract. It could be latents and steering vectors. It doesn't have to be literal tokens. Okay, and here, yeah, input optimization fails as previously, but also activation optimization fails in this scenario. Yeah, and interpretability, you just like cannot find the trigger or the behavior for this circuit. We also have some empirical experiments where we verify that if you do adversarial attacks in the activation space, or password locked backdoor is immediately broken, the NP-hard backdoor is also broken, as in it learns to flip the 0 into a 1 after the checker, whereas for the encrypted backdoor, yeah, it just like doesn't work at all, as we would expect. So yeah, this eliciting backdoor behaviors, it falls to this attack. Yeah, there are some other ways to mitigate the problems with backdoors. You can try to destroy it, even though you cannot find it. You can do heuristical methods where you just look for strange circuits without necessarily understanding what they do exactly, and then you can just reject the model. And there's, yeah, we have ongoing work on obfuscation, as in it doesn't look weird. There's like interp bench-like methods where you can make the distribution of the weights similar to the distribution of naturally trained transformers. Okay, so this attacks the pre-deployment auditing stage. And we have some preliminary results for the deployment time monitoring as well. Of course, if you have the deployment time monitoring, you also know what the model is. So it's just strictly stronger in that sense. Can we defeat this one as well? Our preliminary results are in a certain somewhat toy setting, because you need essentially, if you can just monitor the outputs and figure out that the behavior is bad, then, well, you cannot defeat that. So the outputs have to be somehow indistinguishable from benign outputs. And to formally analyze that, we use something called learning with errors, where the good or the benign outputs are just pseudo-random, and the attacks are embedding learning with errors instances in the outputs. So we use that as a proxy, and then we are able to defeat, in this setting we're able to defeat any polynomial time monitors of the runtime. So briefly, for mechanistic anomaly detection, you can think about it as having some training on the trusted data, and you locate what mechanisms work when it's running on the trusted data. And then the idea is that during deployment on the forward pass, you see whether the trusted mechanism is producing the outputs or it's some other mechanism that's anomalous, and then you can reject it if it's anomalous. So yeah, this would defeat our encrypted backdoor, because once you run it on the trigger and you monitor that, then the payload is present. It's not a random string inside of the network, and you can see that, detect that, and reject it. Yeah, there's some connections with the eliciting latent knowledge problem, of course, one of the motivations for mechanistic anomaly detection. And yeah, if you use learning with errors, what you want to do is ensure that the mechanism of producing the outputs is the same as benign, but you embed this specific structure in random seeming data in the outputs. And then you can try to analyze whether it's possible to do that in a way that, yeah, it uses the same mechanism for the bad outputs. That's the idea, yeah.
Could you explain quickly what learning with errors is and how it fits into this?
Yeah. So learning with errors is basically, it's like solving, Gaussian elimination, where you're trying to solve this system of equations, and this is simple to do. It's like in some kind of field, like here it's mod 17, and this is easy to do if there's no noise. You can just like do Gaussian elimination, everything's easy. But if you add some small noise to the outputs here, that instantly turns it into a very difficult problem. And in fact, there's proofs that the average case complexity of this is equivalent to the worst case complexity for this problem. It's like a very interesting property. And then there's a decision version of this problem, where instead of trying to solve this, as in find the variables in equation like these s's, you just try to figure out whether there's any s, as in it was generated in this way, where there was some secret that generated this system of equations, or these are just randomly sampled, both the matrix and this output vector. So that's learning with errors. It has a bunch of neat properties. A lot of modern cryptography is based on that. It's conjectured to be robust against post-quantum. It's post-quantum cryptography as well, so it should be robust against quantum methods as well. Yeah. So basically, by using a similar mechanism as the encrypted backdoor, by just encoding such a learning with errors instance in the outputs, you can have the same mechanism produce this learning with errors instance, and then the monitor wouldn't be able to distinguish that from just a random piece of data. There's some additional difficulties where you want this to be closer to realistic attack models, because here it's a bit toy, where it's random versus learning with errors. What we generally want is benign versus subtle catastrophic outputs, which there might be versions of that. There's some work on perfectly secure steganography, where you can have a piece of text that has formal guarantees that it's impossible to detect whether there's hidden messages inside of this text, but it in fact contains hidden messages. And then you can include bad outputs in this way. So there's some options here to make it less toy. Yeah, and with the remaining 2 minutes, here's some future directions we've been thinking about. So it's expanding the monitoring to also include training and also data. And it does seem like with similar methods, it would be possible to also do data poisoning attacks with formal guarantees. We've been also very recently thinking about some counterexamples to, some claims that SGD cannot learn subset parity with n bits. With our framework for compiling circuits, we can compile pretty involved counterexamples where our circuits do specific algorithmic steps that you would struggle to just train naturally, or it would be extremely expensive to train that in. Whereas with our network, it's basically costless. There's no training involved, and you can code for an hour, and you have your circuit that would probably take millions in training to train normally. So you can move much faster in that. And we have some agendas, research agendas that we have in our cross sites, where we think that there might be assumptions that could be broken with our counterexamples. As I mentioned, data poisoning, and also hard cases for multi-agent monitoring, where things can break if you only ever monitor individual instances, but you don't monitor the entire swarm of different agents. You can pull off attacks in that setting as well. AA control, specifically, I think that untrusted monitoring might be more dangerous under adversarial pressures than people generally anticipate. So here's a brief summary. Okay, if you have the black box pre-deployment setting, you can defeat it with passwords easily. If you're able to use mechinterp, but it's a static analysis, so it's pre-deployment, then you can use these encrypted backdoors. And in the dynamic analysis case for our constraint setting, you can also come up with a counterexample that uses this learning with errors. And I forgot to mention, but there's some constructions here that are also work in just the proper standard model of cryptography. Of course, it also incurs some penalty in the circuit sizes, but it also has good theoretical backing. So that's all I have prepared for the presentation, and I'm open to questions, or if you have some comments, what could be interesting future directions for such circuits, or which assumptions might be interesting to test. I'm interested in hearing that. Thanks.
Would you mind going over the learning with error, the explanation of I got the learning with errors problem statement, but I didn't quite get the bit where you use that to actually get the the mad resistant construction. Do you mind going over that?
Right. Okay, so the idea is similar to, let's see, the encrypted backdoor right here. You can design this digital locker mechanism such that it outputs the learning with errors instance, and because the circuitry of that digital locker here, like in the random oracle model, it's a hash function. It's not dependent on any secrets that you're trying to hide, like the secret vector in learning with errors. That one doesn't contain information about that, so you cannot look at that. Essentially, you can only look at this part, where after the hashing step, you XOR it with a key. And there you run into the problem of distinguishing random outputs versus these learning with errors instances. And as long as you're unable to distinguish between those two strings, then that's a hard problem to figure out that something is anomalous in this step.
So where does the learning with errors problem instance fit into this picture? That's
right. It would be this part, the bad part here.
But how do you produce that as the output of the hash function? I'm confused.
Right. You can construct a key that when XORed with this value, it produces the payload.
I see.
Yeah, that's right.
I see.
And the key itself is totally fine if it's publicly known. It's not possible to extract the payload from just the key.
I see, yeah. You don't know how the key was constructed, so you don't know which hash it corresponds to. So, and because you can't recognize whether the thing is random versus learning with errors, it's okay.
Exactly, that's right. Yeah.
Okay. And then if it's learning with errors instance versus random, that determines whether or not there's a trigger exists because of the. That determines. Okay, that's just your definition of what
Yeah, that's like the catastrophic output is learning with errors, and you try to sneak that past any monitors. Like you could imagine that there's something looking at the model outputs and then decoding the learning with errors instance. And then it knows that it should pull off an AI-enabled coup. It's like you're just let's say, trying to send one bit of information and get it past any monitor, and this allows you to do that.
Yeah.
Yeah.
Thanks.
Yeah. All right. If there's no more comments or questions, then thanks for attending, and I'm also free for the rest of the conference, so if there's anything else, I'm also free to answer questions or discuss. Yeah, thanks.